So let's keep going. We're in chapter 3. We are going on to section 3.4, which is linear and quadratic functions. Sorry, that was my computer notification, not yours. So in section 3.4, we're still talking about quadratic functions, but we're going to be talking about how to build models from data. Okay, so that's really the goal of the section. Can we build models from data, from verbal descriptions or from actual charts of data? So an example, okay, revenue is defined as the amount of money from the sale and is equal to the product of what are you charging for the item, which we're calling the price P, times how many things you actually sold, okay? It's just the product. How many did you sell and how much did you sell them for? The law of demand states that P and X are inversely related. So as you increase price, demand decreases. If you decrease price, demand increases, okay? So we have what's called a demand equation. When the demand equation is linear, the resulting revenue model is quadratic. Basically, because you are, the demand equation will replace the amount X sold with something depending on the price. So if I have something depending on the price times the price, I may end up with a quadratic function. So for example, the number of units sold X could be given by 18,750 minus 125 times P. So if this is the demand equation, this tells me how many I'm going to sell at a certain price. Express R as a function of P, what's its domain, and then the important question, what unit price will maximize revenue? Okay, remember that the revenue is the product of X and P. So if I take this whole thing and I multiply it by P, what's the domain and what will be the maximum value? So I'll pause here while you try to answer that. So the easiest mistake to make here would be to say that R is 18,750 minus 125P times P. In other words, it's 18,750 minus 125P squared. If you started this way, you made a mistake. Okay, you have to take all of X and multiply it by P. So it's 18,750P minus 125P squared. If you made that mistake at the beginning, pause again and finish the problem using the correct revenue model. Okay, otherwise we're going to keep going. So there's other questions to ask. If the price is charged, once we determine what price should be charged to make the maximum revenue, what is the maximum revenue? How many do you sell at that price? Can you graph the revenue function? And then ask what prices will give me at least $590,625 in revenue. Okay, so if you've already done A, B, and C, okay, as long as we started with this as our revenue function, as a function of price, our revenue should be 18,750 times P minus 125 times P squared. Go ahead and complete the rest of the problem. What's the domain? What price will maximize revenue? Copy down this function, 18,750P minus 125P squared. I'm going to go to the next slide. At that price, what is the maximum revenue? How many units are sold? Graph the function, and then ask what prices give me at least 590,625. All right, so there is our demand function, 18,750 minus 125P. Once we multiply out by P, we end up with, as stated before, negative 125P squared plus 18,750P. The way I wrote this, by the way, was 18,750P minus 125P squared. It's the same thing. Just note, as a quadratic function, A is negative 125. Even if it's not the number that's first, it's the number multiplying the P squared. Okay. So the book writes it in this sort of standard order so that you get A and you get B and you get, so B is 18,750 and C is 0. There isn't a term without a P in it. I would tend to in this form because whenever there's a negative sign on the first term, I can easily miss it. Just visually, I tend to accidentally omit that. So I try to avoid putting negatives first because otherwise I start making mistakes. It's really a matter of personal preference. But the book is going to put it in standard order down here. This is with the squared term first. So the question was, what's the domain? Now, a quadratic in general has any domain you want, but the number of products sold can't be negative. It doesn't make any sense to say, well, I'm going to sell negative 20 units. I'm not going to do that. I'm not going to buy back units. So we need x to be positive. Now remember, this was x. So I set x to be bigger than or equal to 0. If you then move the 125p over, you get 18,750 should be bigger than or equal to 125p. Divide by p, and you get p is less than or equal to 150. So if I charge more than $150, the number of units sold by the model would be negative, and that doesn't make any sense. So I'm going to cap the domain at 150 bucks, but I also need p to be positive. First of all, I don't want to charge a negative price for something. That doesn't make any sense. So you could see it that way. You could also say you need revenue to be non-negative. And for revenue to be non-negative, you need this quantity here to be non-negative. And then you'll get p needs to be bigger than or equal to 0. Okay. So altogether, the price can go between 0 and $150. It doesn't necessarily make sense to charge $0 for the item, but it's at least an allowable input. Okay, so here is our quadratic function r. A is negative 125, b is 18,750, c is 0. Because remember, we had r of p is negative 125p squared plus 18,750p, and then nothing else. So there is no c term. That's a p, sorry. So because the a term is negative, it's concave down, which means the vertex is a maximum. Our revenue will be maximized. So let's find where that happens. Negative b over 2a, well, there's our b and our a. So I get negative 18,750 over 2 times negative 125s. The negatives cancel, and 2 times 125 is 250. This divides out quite nicely to be just $75. Okay, so at $75, our revenue is maximized. What is the maximum revenue? Plug in that maximizing price. This is not something we do by hand, but a calculator quickly tells us it's $703,125. If I plug in that maximum value price of $75, we get out $703,125 in revenue. The next part asked what prices will give us revenue over a certain amount. Okay, so. Oh, sorry, the next part said at that price, how many are sold? So the demand function was 18,750 minus 125p. So if I plug in $75, we get 9,375 calculators sold. So here is the plot, and there is its vertex. Okay. The next part did say, so we're just going to graph the same thing. Where is the revenue bigger than this? Okay, so our graph looked something like that, and we know that this caps out at 75, it was like 700,000 something. So 590,000 is going to look something like that. There's going to be a range of prices that give me revenues over 590,625. So we need to find where these intersect. How do I find where a parabola intersects a line? I set them equal to each other. Okay, let me clear out my pen marks. So by setting the revenue of negative 125p squared plus 18,750p equal to the target of 590,625, we're going to move everything over to one side. And now I have a different parabola. Okay, I have a different value of a, b, and c, but I am trying to find where is it equal to 0. So okay, we could go right to the quadratic formula. You might notice, however, that everything here is divisible by 125, which will make our computation a lot simpler. This is an optional step. If I divide everything by 125, the numbers become a little smaller. Okay, look, I'll be honest. No one is going to stare at this and be like, obviously 4,725 factors as 45 times 105. Everyone would just throw this into a calculator and apply the quadratic formula, and would get 2 roots. Okay, if I do the quadratic formula, we're going to get p is either 45 or p is 105. Sorry, 105. And then you would know if those are the 2 roots, this is how it factors. But either way, we get 2 different values of p. Okay. So the two intersections are from 45 to 105. So now that we've identified the prices at which our actual revenue parabola intersects the horizontal line of, I want the revenue to be 590,625, what prices will produce revenues bigger than that? Everything in between 45 and 105. So if I set a price to be anything in between 45 to 105, then I will have revenue bigger than 590,625. And we see that just from this portion of the graph. Okay, second example. Suppose a farmer has 2,500 yards of fence. It's going to sound like a totally different problem, but it's going to actually work out to be fairly similar. I have 2,500 yards of material, and I want to enclose a rectangular field. How can I make the most area? Okay, so notice I'm going to draw out a rectangle with my fencing material. It's going to have a certain height and width. So how much fencing I have is the perimeter of the rectangle, which is 2x plus 2w, and I want that to be all the material, 2,500 yards. Okay, but what's the area? X times w. So I have two equations here. It looks like we have two unknowns, w and x, but we really have two equations, and we're going to play that to our advantage. So if the area is x times w, okay, notice that 2x plus 2w is 2,500. This came from the perimeter. I can subtract the 2x and divide by 2 to get that w must be, so this w here is actually 1,250 minus x. So now I have not two variables, x and w. We have a single variable, x, and then the other side length must be 1,250 minus x. So then the area, x times w, turns into x times w, which distributes and rearranges in standard order as negative x squared plus 1,250x. Now the question is, what choice of x will maximize this area? If I can find the value of x, then I will also have found w, because it's 1,250 minus x, and I'll know how big to make my rectangle lengths to get the biggest area possible. So we have a quadratic function. So a is -1 and b is 1,250, and what's c? 0. There is no constant term, just like in the previous example. So here is a graph of this parabola. Can I find the choice of x corresponding to this vertex? So again, I have a concave down parabola, which means I'm going to find a maximum area. So I find that vertex at x equals -b over 2a. I plug in my value of b and my value of a. The negatives cancel, and we get 625. So at x equals 625, I'm going to have my biggest possible area. So what is the maximum value? I just take that value of 625 and I plug it into the corresponding parabola. And again, we'd ask a calculator to do this because it's a little large to do by hand, but we end up with 390,625. And what units are going on here? So remember, when we measured our perimeter, we were measuring in yards. So x is measured in yards. What about w? Also yards. So what's our area? It's the product of x and, sorry, not y, w. It's going to be square yards. Okay. So the largest rectangle is 390,625 square yards. Notice if x is 650, w was 625. X is 625. W was 1,250 minus x is also going to be exactly 625. So if I made x 625, I also made w 625. So this wasn't just a rectangle, it was a square. That's supposed to say square. My handwriting is terrible. So if you want to make a rectangle that encloses the biggest possible area, if there's no other restrictions going on, you make a square. Okay. I'll switch over to a new video just in the interest of time, and then we'll move on to example